Good day, everybody, and thank you very much for attending this, our latest in a series of webinars. ProTech is running these Lunch and Learn webinars at a pace of every 3 to 4 weeks. We greatly appreciate your attending this one on real-world security issues within machine learning. My name is Tim Noka. I'm second chair today. The smart guy in the room is Rod Davison. I'm going to introduce Rod in just a second. If I could, I'd like to just take a moment or two at the beginning to talk about some practicalities. This is a webinar by which we invite many people in, and if we were wrestling with microphones back and forth, it could be awkward and take longer time than we all have for a lunch and learn style webinar. So at the same time, though, we do want you to be able to participate. If you have any questions, please do not hesitate to put them into the question area of the webinar. In order to see that, it's possible that your webinar software has been tucked away in the upper right-hand corner. If that's the case, hit the arrow that's pointing out towards the screen. Within there, you should see an area for questions. Please go ahead and type your questions in there at any point that you have them throughout the webinar. The way we're going to roll is that we're going to take this webinar up until 30 minutes after the hour so that we make sure that we give you all the content that you signed up for. And after that, Rod and myself will stay. I will verbalize the questions. He will answer them. We'll stay until we're out of questions. So with that, let's go ahead and get started with a quick introduction to Rod, and then we will give him the mic. Rod Davison has lots of experience out there in the world, 10 years working in civil engineer testing models and methods, and total quality management and QA and industrial developments. 30 years working in social science research and testing with 10 years in medical testing. 30 years working in software testing and quality assurance. 10 years working in market research building testing models. One of the things that we like to assure you of is those years are not sequential. Rod has overlapped them, all that experience quite a bit throughout his career. Otherwise, he'd be a very old man. Rod has been in and around AI since 1984, has been active with it that whole time. So he is experienced, but he's not an old man. And with that, Rod, we'll go ahead and give you the microphone to lead us into real-world security issues here. Thank you, sir.
Thank you very much, Tim, and welcome everybody to this webinar. This topic is a little bit unusual in the sense that it's not a topic that's discussed a lot out there, and I was just mentioning to some people earlier that I can't really find anybody that's currently talking about this, or at least publicly, which makes me suspect that if people are being concerned with it, it's being discussed behind closed doors. So hopefully we'll shed a little bit of light onto this. What we're going to talk about is what I believe is a very real concern as machine learning in particular and artificial intelligence systems in general start to get deployed into operational environments, whether it's government or corporations, that we haven't taken into account the risk of attack from hostile actors. And this is paralleling a scenario that we saw earlier with the internet, where we didn't think about it until it was really too late. So we want to try and learn from experience. And in this seminar, I'm going to basically go over the basics of what we call InfoWar, which encompasses cybersecurity, but it's a much broader topic, and talk about the machine learning scenario we're looking at now, what we mean by the vulnerabilities, and some ideas about where these vectors of attack are, and some of the things we may be able to do to mitigate the risk. So first of all, we'll get the notion of InfoWar. InfoWar is not cybersecurity. It encompasses cybersecurity. Cybersecurity is a special kind of InfoWar. InfoWar in general is the attack and on and exploitation of IT infrastructure, resources, and systems. And this could mean from subverting a company's organization by bribing a programmer to install malicious code, to disrupting their development process. Any place that we've got an IT infrastructure that we can attack in some way, then we have an InfoWar situation. And this can include things like social attacks on IT staff, the famous social engineering kinds of attacks. An example of InfoWar would be bribing somebody to get into the computer room and then turning off the air conditioning so the computers all melt down. It's an attack on the IT infrastructure. And this is often part of a larger initiative by these hostile actors to accomplish some sort of value target. Now, the types of InfoWar that we look at tend to fall into, or the participants tend to fall into three categories. The first one is the independent hacker. These are people who are often disgruntled employees or some other kind of disaffected individual, or maybe somebody who's got a political agenda or something else that they want to establish, and they decide to accomplish their objectives through some kind of InfoWar attack. Number 2 and 3 are often lumped together. We've got organized criminal activities, and we're familiar in the cyber warfare situation where people go in and loot credit card numbers and information, for example, or the famous Ashley Madison attack. It was an independent hacker attack, but also could be called a criminal attack because somebody was trying to extort that for ransom. The ransomware that we see where people get their drives encrypted is an example of that level 2. Level 3 is where a company is using InfoWar as a means of establishing a competitive advantage over the competition. And we kind of put 2 and 3 together because very few companies will directly be identified as an instigator of InfoWar. Instead, they'll usually operate through some criminal proxy that they've hired to do that. So we kind of lump 2 and 3 together. And number 4 is InfoWar by nation states, which are attacks on their infrastructure. And of course, that's been in the news a lot with the North Korea attack on Sony, for example, attacks on the American infrastructure and other countries' infrastructure as well. So we do have a number of InfoWar types, and all InfoWar operates on the same kind of security model or risk. First of all, there have to be vulnerabilities. There have to be points at which your opponent is weak, where your attack will succeed. Generally, in cybersecurity, if you think about points of attack, it's through a company website that hasn't been locked down properly, failure to use proper passwords, failure to get people up to speed on an appropriate security protocol. All of these represent vulnerabilities that can be attacked. The opportunity or exposure is the accessibility to the attack. The more you make these available in terms of exposure, then you increase the opportunity for people to attack it. So people couldn't really attack bank systems that well before the internet because you had to actually physically get onto the bank system. But once they got pushed out to the internet, you started to create opportunities to be able to move into these systems. And value, generally, or I should say, once the IT systems start to have things of value in it to the attackers, then they start to become payoffs. Very few people who are engaging in info warfare are doing it just simply for the sheer fun of it, although some hackers do. Mostly there's some underlying value that they want to get or payoff for that. Now, the model that I'm using here is what we discovered with the early internet. And I kind of lived through those periods. And the early internet was developed in a university corporate environment. And it was a lovely community of people that were motivated and they're being innovative and inventing all of this new stuff. And nobody thought about security because it wasn't really necessary to think about security at that time because, well, you know, that's just not what we're into. It's an academic exercise. We have this idea of collaboration. In fact, I remember when at one point it was suggested that people actually use passwords on the internet. There was almost a riot amongst my colleagues who said that that was a horrible, that sullied their integrity to think that they would have to lock things down with the password. Makes me very naive now at this particular point. But the other thing was that because of the restricted range of the internet, there weren't a whole lot of opportunities for people to get into it to do any kind of damage. The Morris worm, for example, in the 80s was brought down the early internet, but that was because somebody inside the internet was actually doing a little experiment and got away from them. The other thing was that there was generally nothing of value that a criminal gang or a nation state would want necessarily There was no a payoff to actually breaking into some professor's computer system. So all of these this combination of factors led us to this relatively naive model of everything's fine. We don't have to worry about this. And it was valid in that context. But then we pushed it out to the internet. Because we hadn't been doing a lot of testing and we hadn't developed a really solid quality control and quality assurance model, all of those vulnerabilities that were in the early systems were pushed out onto the internet as well. And that meant that suddenly we had all kinds of vectors of attack or points of failure that could be exploited by an adversary. Pushing it out onto the internet, of course, also increased the exposure. Now people can get access to those points of vulnerability. And when we started to do things like process transactional accounts online, do banking online, suddenly we've got the data and operations that could be accessed to have value payoff, and they make attractive targets to the various criminal gangs and that sort of other sorts of dimensions of info warfare. The net result now, as we look around today, cybersecurity is a major problem because we didn't build it into the internet from the beginning. We're kind of playing catch up with that, and that is sort of a lesson to be learned. So, for example, quick examples, here's Gary McKinnon was an example of that kind of level 1 hacker. He broke into the NASA and DoD computer systems looking for information about ETs, extraterrestrials, and UFOs. So that for him, that was a value. Sometimes very hard to predict what's of value for some of these people. But what was really disturbing is he broke into NASA quite easily, apparently. And of course, you Google Gary, you can find some interesting statements that he's made about that. JPMorgan Chase had a breach into their system in 2014, I believe. 76 million households and 7 million small business accounts. Chase was very secure, but this is, in the last line, it's a national crisis. We're all under attack. It's not isolated. Chase said, don't worry, they didn't do anything, even though they were in our system for months on end. What Chase is really saying is that if they did something, we don't know what it was, or they haven't done anything yet. And similarly, we're seeing that once people start to think in terms of breaking into systems, the shadow brokers leak has allowed people to get their hands on a number of tools which make the situation even worse from a cybersecurity perspective. But even more interesting is this an example of a nation-state attack where the Office of Personnel Management was hacked into, and for months, all of the what it says SF-86 forms, which are used in applying for security clearances, all of those were downloaded, contained all the dirty secrets of everybody who's applied for security clearance. And we suspect there's a database in some country somewhere of all of these people with all of their points of vulnerability. Okay, in other words, what we're saying here is that failure at security at the internet level has produced some really, really bad results. And we're not going to talk about that anymore, but using that as an example of a sequence of actions that I am suggesting could be repeated now with machine learning. And there's George Bernard Shaw saying, hey, you got to learn from the past. If we don't learn from our experience, we're going to wind up in the same situation. Machine learning is sort of in a similar situation of the early internet. Right now, there's a lot of focus on innovation. People are excited by it, its capabilities. And I have not seen a single discussion about security of machine learning systems. It's generally have been used in experimental settings where we've got great successes. You can go onto the internet and Google machine learning and find thousands of pilot projects, limited applications, all kinds of interesting innovations that are being done. People are very excited. But there doesn't seem to be a whole lot of things necessarily that are of value to attack. Well, at least they don't appear to be. What we're finding now is that machine learning is starting to be deployed back into the corporate and government world, and it's being applied in such a way that these are going to become targets of value. The vectors are wide open because we don't do any significant QA or testing to evaluate the vulnerabilities. So history could repeat itself. So let's put a hypothetical scenario in place. What if you could corrupt a company's business decisions? In other words, if they're relying on a recommendation system or they're relying on some kind of decision support system, what if you could rig that system. So they always made the wrong decisions, and you could have a competitive advantage. What if you could rig decisions like loans approvals? So if you're using some kind of machine learning system to do some kinds of loans approval analysis, and you could rig it so that you could get people to get loans who shouldn't get loans in order to rip off the system. What if you create holes in a fraud detection system so that certain specific kinds of fraud that you would engage in couldn't be detected by this system, would be blind to it? What if I could manipulate a hiring process and get my people into key points in an organization where they could do some kind of damage or corporate espionage? What if I could break into a machine learning system and corrupt their data models so that any kind of strategic planning they did on the basis of that was wrong? It became useless. What if you had machine learning that ran a company's operations, and I basically was able to muck up with their machine learning models and turn the company's operations into chaos? As more and more government functions and business functions are migrating to machine learning systems, what this now produces are high-value targets. Those are now suddenly going to be attractive to various kinds of groups out there. This is falling into a category now of what Grady Bush called mission-critical software, which basically says that when an organization becomes so dependent on its software that when the software fails, the organization can't function, we've got mission-critical software. And when it gets to that point, also, it's so large and vast, it becomes industrial-strength software, and nobody can really understand all of it, or no one person can understand all of it. And our machine learning systems are moving in that kind of direction as they take on more and more kinds of operations. So, for example, here's an example of using machine learning in Queensland, Australia, to identify possible points of failures on their electrical grids. Well, what if I could muck up that machine learning model so that it wouldn't detect the points of failure that I am engineering in there to create some kind of terrorist attack or some other kind of engineered failure to the system? All right, so I can make the system blind to what I'm doing. FinCEN and other organizations use machine learning and data mining to look for patterns of fraud in various kinds of financial transactions. And this is very difficult to do because people are trying to hide their trails, and so there's no overt sign sometimes of fraud, but you find deeper patterns that you can go and track down. What if I could get in there and subvert those machine learning algorithms so that they would become blind to certain patterns of fraud that I'm engaged in? In other words, we could do something behind the scenes that nobody can do. Or Uber Eats. Uber Eats uses machine learning in its operations. Well, if I'm in competition of Uber Eats, maybe I could get in there and screw up their planning system in order to make customers really, really unhappy and give me a competitive advantage. Those are, and of course, the final example that I find a little bit scary is people are talking about making machine learning responsible for deciding when to launch nuclear missiles. I hope they never go this way, but suddenly that's a really high-value target when you stop and you think about that. That's just a little example of sort of the potential that we've got here for bad things to happen in our machine learning and AI environments. Okay, so again, we're seeing a repetition of what we saw in the past with the internet. We didn't think about security. We took a naive point of view. We're going to roll out. We're going to do great things. Everybody's going to be happy. We're going to empower businesses. We're going to make things more efficient. And we didn't stop to think that there's a lot of predators out there who are just waiting for an opportunity to exploit what we put out there. We found out that really fast, and now we're playing catch up. So we've got a similar kind of mentality going on in our machine learning. One of the first things, and I stressed this in another previous webinar, is that the first kind of mitigation that we need to do is to really start developing a solid protocols and procedures and overall methodology for thinking about testing machine learning systems in order to identify points of vulnerability. And of course, Boris Beiser has one of the great comments, one of the great gurus of software testing. He said, more than the act of testing, the act of designing tests is one of the best bug preventers known. And here we can think about bugs as being points of vulnerability. The thinking that we have to do to create a test can discover and eliminate bugs at every stage of the creation of software, from a conception to specification to design, coding, and the rest. If you can't test it, don't build it. If you don't test it, rip it out. This is true for almost every system that we've got out there. The truth of this has been shown over and over again, but we're not doing it in machine learning. We're not doing it in AI. Or if people are, they're not talking about it at this particular point. Now, there are, and I mentioned in a previous webinar, that we can do this. The technologies, the tools, the methodologies are there, being used in other disciplines. We just have to now apply those to machine learning. Let's take a look at some of these vulnerabilities and how they can be exploited. And then we'll look at the specific attacks that could happen. This is an example of the IBM Watson supercomputer, and not all of these are strictly machine learning, by the way. And they were doing patient cancer analysis recommendation systems, and the doctor said this product is a piece of, and it's bleeped out there, wrote a doctor, Florida's Jupiter Hospital, and they said that the AI health did not impress doctors. It gave wrong recommendations on cancer treatment that could cause severe and even fatal consequences. The reason for it was that they trained it on hypothetical data, not real-world data, which goes to show that if we could somehow put the right data into the training models, we can make systems, the machine learning systems aren't intelligent. They don't know that they're wrong. They're just going on the basis of the data. We could subvert some kind of decision-making system by manipulating the kind of data that goes into it. So if this was done accidentally, this was an error. But again, every time we have an error, we have a point of vulnerability which can be exploited by an adversary. Another example is Amazon scraps the secret AI recruiting tool that shows bias against women. So what happened? It turns out they had misogynist software. It said everyone wanted this. One of the people said they literally wanted to be an engine where I'm going to give you 100 resumes and we'll spit out the top 5 and we'll hire those. Unfortunately, again, because nobody thought about the kind of data that was being used to train the model, they trained it on previous historical data, which had generally in the past tended to favor males because of various kinds of biases in the hiring process. And all we did was institutionalize that bias, so they finally got rid of it and realized, okay, that's not working for us. What if we could actually bias like a fraud detection system, so that we could have it ignore certain kinds of examples of fraud, so it would become blind to those kinds of fraud? Again, thinking from an adversary. One of my favorite examples is a hiring algorithm that when they actually examined it, discovered that the algorithm decided that 2 factors that were most indicative of job performance was that the candidate's name was Jared and that they played high school lacrosse. Okay, we've got to kind of take a look at maybe not necessarily the data, but take a look. And this sounds like there's an algorithm issue here. So maybe somebody didn't do the due diligence on the algorithm. But that suggests too, if we could manipulate an algorithm, maybe we could make it recommend people that we wanted that were not necessarily the ones that the algorithm was supposed to recommend in its original specification. So maybe, for example, maybe we want to get somebody at that company named Jared who played high school lacrosse, who's going to act as a corporate espionage agent for us. The other thing we discovered, we get a lot of comments about the machine learning failures for facial recognition. The main reason why we're seeing these failures is because it developed mostly to build models based on white male faces. So it has a very bad rate of success with minorities and women. So we tend to find that we got a 0% success rate at identification here. And also we get a misidentification of 96% of innocent people as criminals in England using facial recognition. Well, that suggests that it may be possible, again, by selectively choosing the data we train the models on, is that we could get certain kinds of results that we want when these systems are deployed to make decisions. Again, it's biasing and creating the models that do what we want. Another example is that Microsoft's AI chatterbot, Tay, became a racist, misogynistic, genocidal psychopath after a couple days of training online. Imagine what we could do if somebody has these chat systems for customer support. We could turn them into copies of Tay and basically create a great scandal for that organization, maybe their competitor in the marketplace. So there's a lot of different opportunities. As we can see here, that was a list of where a lot of these systems went wrong. And these weren't attacks. These were just because we didn't think through what these vulnerabilities and what these problems could be. So the fundamental rule of security is every time you have a vulnerability, you have a vector of attack. So let's just kind of take a look at what some of those vectors of attack are. Well, this is the standard machine learning process. We start with some raw data, we choose it, we pre-process the data, which means we do data quality, cleaning, analysis, look for weight the data depending on how valid it is, and we do data quality measures. And then that prepared data is then used to train an algorithm. We're going to pick an algorithm, we're going to train the algorithm, and from that we're going to get a model, which is going to be the basis of the machine learning, which is going to be used to help us make the decisions. And then we're going to deploy that model into an environment, and then we're going to use that model in various applications to produce results or predictions or make decisions, whatever it happens to be. Now, each one of these steps in the machine learning process represents a vulnerability. So, for example, choosing the data. One of the examples that I came across was that if you use any of these loyalty cards that are issued by stores, what they're trying to do is create profile patterns of your buying patterns and buying preferences so they can target you for advertising and that sort of thing. I came across a group of people in New York who all had these loyalty cards, and they basically rotated the cards amongst themselves every couple of weeks so that they were basically poisoning the well and preventing people from developing any buying patterns. They wanted the loyalty cards, but they didn't want the profiles. I don't know how successful they were, but I find it very interesting that people often will tend to do this. We also noticed that a lot of these models failed because they were trained on, in the examples we looked at, trained on data that wasn't representative of the population. So until we get some really good sampling protocols in place to ensure that the data we're choosing is actually representative of what we want to work with, there's going to be that opportunity for people to fudge the input data so that, for example, if we're looking at fraud analysis, we might just decide to not choose data from certain places or certain systems so that that data about fraud never makes it into the model. Okay, so there could be selective data choice and selective data manipulation, selective data omission that takes place at that. Plus, we're assuming the data is valid. We don't know about whether or not that is actually true. There's a fascinating book in which people compared what people said they searched for on Google versus what they actually searched for on Google. Most people talked about, well, I use Google to find out this or that. So in other words, we don't necessarily know how good this data is that we're building models on. When we pre-process the data, we're cleansing the data, transforming it. Now we could subvert that by putting into our transformation process little bits of code, for example, that might just not let certain data, even if it's collected, get into the data that we're going to use to train. So we might decide that if we're doing a fraud detection system, we're going to delete all of the data that refers to fraud that is associated with our particular organization. So it never actually shows up in the training data. So if somebody says, what's the likelihood of fraud from this organization? Well, we've kind of expunged that from the training data, so it never shows up in the predictive models. So the next thing we do is we choose an algorithm. What if we could get somebody to choose the wrong algorithm so it had really bad predictive capabilities? In this particular case, if this is deployed out into an operational environment like Uber Eats, we might be able to completely screw up their business operations by maybe bribing the people who are in charge of doing the algorithm. Maybe they're applying the algorithm in an incorrect way and producing multiple candidate models and then choosing a model that is not efficient or not actually meeting the organization's best optimal for the organization, but represent some kind of subversive result that we want to put in there. Okay, so in other words, at any one of these points, we can inject some kind of attack. Deploying the model, well, maybe we'll just deploy the wrong model. Maybe we'll actually build a model, but we'll build our own model in as well that does what we want. And when it comes time to deploy it, we won't deploy the real model. We'll substitute and deploy our model in order to subvert the whole decision process. We've built this model somewhere else, and now we're going to drop it in here as kind of a substitution. Now, the other thing that we have is that we're going to actually use an operational environment. Maybe we can disable some of the things it does in terms of its queries. so that we actually get down to using the applications, it's not even going to be able to exploit what's in the model. Now, I've just presented these hypothetically as examples of where we can get various kinds of attack taking place. And these are all well-known sorts of attacks that we look from other security areas. So, for example, one of the great failures before the computer era of profiling and doing decision-making systems took place in 1972 in May on what's called the Lod Airport Massacre, in which there was an attack on the Lod Airport in Israel, in which I think it was 26 people died and 80 were injured by terrorists. And the reason that attack succeeded was that the Popular Front for the Liberation of Palestine was under very, very close scrutiny by the Israeli authorities. And there was literally nothing they could do. They had it locked right down. The Israelis were really, really good at preparing the profiles that they used to decide who to search, who to let in. So the PLPF knew that they were being profiled with this data. So what they did was they subcontracted the terrorist attack to the Japanese Red Army. And they were able to slip right through security because the Israeli authorities were not looking for Japanese terrorists. They were looking for Palestinian terrorists. And that's an example of the kind of I'm not going to call it bait and switch, but that's the kind of deceptive manipulation that you can do once you know what these models are, how they're being constructed and how they're working. So that was 1972. So that was before we had any of this technology. But again, the strategy is the same. Let's face it, criminal behavior doesn't change that much over the decades. It's just that we're presenting a new opportunity for them here. Okay, so Elon Musk, as much as you might like his cars, has said, and I'm not sure if he's being prescient or being paranoid, and he says with artificial intelligence, we're summoning the demon. In a certain sense, we found that with the internet. And we talk about mitigating risk. Well, how do we mitigate these potential risks? And I'm going to say, and I'm going to go out in line and saying these risks are real, they're there. It's the same people that have committed these kinds of attacks in all of the kinds of vectors, including cyber attacks and everything else. They're just looking for opportunities to exploit our vulnerabilities once we start to get these systems out there to get those high-value payoff targets. So how do we mitigate it? Well, the first thing we have to do is close down the vulnerabilities. We have to implement a really strong sense of software, machine learning, quality testing, and assurance, and to identify the vulnerabilities, including sampling errors and all of those other sorts of things we just pointed out. The second thing is that we have to apply, we've got a really, really good security models that are out there, standards and policies, and we have to now take those and apply them to artificial intelligence applications, including machine learning, because we now recognize that they should fall under that security model, which means that we have to think about these the same way we think about other systems. The same kind of security models that we use should be applied to AI and to machine learning. So we've got the tools. We know how to do this. The problem is we're not doing it. Now, I suspect some people may be doing it, but they're doing it often behind closed doors. They're not telling anybody they're doing it, which is probably a good idea. But the point that we want to make here is that we have a potentially really dangerous situation on the horizon as we become more and more dependent on AI and ML systems, as they become mission critical software. Until we remove the vulnerabilities and deal with it from a security perspective, we are really leaving it open for a real attack to succeed in a way that could have devastating consequences. So the end of this seminar or webinar is just basically to say, we've got a potential problem. We know how to solve it, but what we've got to do is actually make the decision as both an industry and as organizations who use these systems to actually address the problem and create a highly secure environment for our machine learning systems to operate in. And that's it for the presentation. I think we're just a few minutes over. So Tim, we'll turn it over to you for questions.
And I do have a couple. If you could do me a favor, Rod, put up the, I want to, before we get into questions, that slide.
All right.
So just for everybody's information, we do have some upcoming courses that are related. This is kind of a high-tech and very very leading edge topic. So we have related courses, not necessarily courses yet that are dead on. I also want to mention that we do, excuse me, on our website, if you would go to the resource part of our website, you can see all these webinars that we've brought up a couple of times now. The ones that are in the past are on our YouTube channel, and you can get to them from there. You could sign up for the ones that are in the future as well. The next one that we have coming up is on Linux, and it is December I've lost it in my notes. I think it's December the 16th. But again, check our website. My apologies for that. Here it is. Yes, Monday, December the 16th at noon. Questions? I've got a couple right now. As we ask these questions, those of you that are sticking with us, please don't hesitate to send in more. First one, Rod. It kind of seems like this threat is not being taken being taken seriously. Can you give us a sense as to why that would be the case?
I think there's a couple of reasons for that. I think reason number one is that the threat is not being perceived as serious because either, number one, these attacks have occurred and nobody wants to admit that they've been the victim of an attack, just like people don't want to admit to being a victim of a cyber attack. Number two, we haven't actually, the other possibility is that we may actually be a little bit ahead of the curve, and we haven't seen a major attack of the kind that'll suddenly create public awareness. Like if somebody could get into the machine learning algorithms or automated self-driving cars, and suddenly they all crash into each other one day, that would draw public attention to. We haven't had that kind of laud massacre type of event. And the third reason is that this may already be happening, but nobody notices. Just like at the JPMorgan Chase example, they were in these accounts for 4 months, these hackers, and they couldn't figure out what the hackers had done other than just kind of stroll through the system. So we may already be seeing these attacks, and they're being done in a very sophisticated and stealthy way, so that our systems are already compromised, but we just don't know it yet because we have no ways to detect that they've actually taken place. So it's more kind of we're not seeing it, so it's not in anybody's uppermost in their awareness.
Nice points. Appreciate that. Machine learning is already being deployed, and it's coming at an increasing rate. Is there anything that an organization that you would, I mean, to a certain sense, this has been the whole webinar, but anything specific you would recommend an organization to do to guard against attack in their machine learning and in their AI systems?
The first thing I would suggest is that evaluate your corporate security policies. Look at your policies that you have for all your other systems, your web systems, your systems of record, your database systems. And if you don't have one, start there. Get one in place. And then extend that corporate policy to cover any of your machine learning decision-making systems, and very specifically encompass it with policy. The second thing that you have to do is to develop a quality assurance program for your machine learning systems where you actually go and test for the vulnerabilities at various places, and then you put into place barriers or patches to prevent those vulnerabilities. For example, I mentioned poisoning the well. Well, one of the things that might be a policy is to ensure that you've got appropriate sampling techniques and data validation to ensure that the data that's going into the machine learning system is in fact good data. So I would say, number one, if you don't have a security policy, get one. If you have a security policy, extend it to cover AI systems. Number two, if you have a quality assurance program for software and systems, extend that to encompass your systems. I think those are the two most obvious and immediate effects that you can have, or actions that you can take to mitigate the potential for attack.
Okay, excellent. I'm out of questions, Rod. Anything else that you would like to add before we close?
I would just say that anybody out there who might be running machine learning systems, I would start to encourage you to think in a little bit more of a paranoid way about what's going on in your systems. And don't be afraid to poke or prod to make sure that, in fact, it is doing what you really think it is doing. And that's probably another point I'd want to make.
Nice tip. I appreciate that. So again, thank you, Rod, for coming and doing this webinar for us. Thank you, everybody that came to attend. It's greatly appreciated. Look out for, in the near future, we'll have the slides and a recording of the webinar that we will be able to distribute, and we will write to you as soon as that's available. Thank you all very much. Have a great day.
All right. Thank you all for your kind attendance.